Hi everybody, we're continuing with our Chapter 7 notes on friction and inclined planes. And up to this point, we've talked about friction as just kind of another force that is acting against all the various forces that we've been summing up. But now we're going to actually be able to calculate what friction is and how it changes as other forces change. And so that's what this part is going to be on. We're going to do one example. That example is going to be example 7.3, this right here. But we'll get to that eventually. So what is friction? What actually causes it? Well, first of all, it is a force that doesn't exist for its own sake. It simply exists to oppose other forces. All right, why does it do that? Well, because all surfaces have microscopic little hills and valleys that catch. And these little hills and valleys right here tend to resist movement. So friction doesn't act unless you try to move something. So if you apply a force to this upper block right here, friction, I should have made that a different color. We'll make that green, all right? I'm going to apply a force to make it go, to move the box right there. Well, friction is going to act, at least to some degree, against that. I'll just call it F sub R for now, but we're going to give it a different subscript a little bit later on. Just the right amount of it acts, well, I should say a certain amount of it acts to resist your force. And if your force is great enough, it'll overcome friction and you'll finally get the box to move. But friction is a resisting force. If you don't have an applied force, you don't have a resisting force. But if you, as soon as you start applying a force right here, the friction force comes in and acts against it up to a certain point. All right, so the first kind of friction that we're going to talk about is called kinetic friction. This is the friction of between two surfaces when they are in motion past each other. All right, like I said before, friction opposes their motion. And so if you have let's say you take your calculator and you slide it across your desk, all right, you'll notice that you keep having to apply a force because your desk is going to be creating friction between it and the calculator to resist your force right there. And so this tendency of these two surfaces to exhibit friction is dependent upon one big thing, and that is the coefficient of kinetic friction. All right, and so what a coefficient is, you probably know from math, is simply a number out front, you might say, or it's a multiplier. Well, the coefficient of kinetic friction is this Greek letter. It's called mu. M-U, that's how you pronounce it, mu. Okay, some people say moo, like a cow, but I say mu, all right? And it looks like a U, like a lowercase English U with a little tail on the front right here, all right? But we're going to put a little K next to it. So mu sub K, or mu K. All right, what is that? That is a measure of the, for lack of a better word, the frictioniness between the two surfaces. Or you might say the roughness between the two surfaces. All right? So, how does that help us find this friction force right here that acts? Well, remember how I said before that we called friction just F sub R? Okay? Well, now we're actually going to be calculating it, and we're going to be calling it F sub K. This is kinetic friction. That is friction that acts between two surfaces that are in motion. And that is calculated as such. It's the coefficient of friction between them, mu sub K, times the normal force. That's it. Now, if you think about this for a second, the normal force is the force, you might say the perpendicular force between the two objects, right? And if, let's say you're moving your calculator across the table, what if you were to put something on top of the calculator like another calculator or an apple or a bowling ball or whatever? You're increasing the normal force. And so what that does, if you're increasing that, that makes there be more friction, right? Because there's more pressure, you might say, pushing between the surface between your calculator and the desktop. And so that's going to increase the friction. So the coefficient doesn't change between two surfaces, but the normal force just might. and that is what will increase your friction. So this right here, box that is our calculation for calculating the force of friction. It's mu k, coefficient of kinetic friction, times the normal force. That coefficient doesn't have any dimensions. It's just a multiplier. All right, it's simply you might say well, like I said, a coefficient out front. All right, it tells how much that normal force is going to translate into a friction force between the two surfaces that is opposing your motion right there. You actually can't even calculate it. You have to determine it experimentally, and if all goes well, we'll actually get a chance to do that in lab. We're going to be measuring the coefficient of friction between various surfaces, maybe like a nylon slider, or maybe sandpaper, or maybe cork, various different things. So you can't actually calculate it. You must experimentally determine it. All right, and it really determines on how rough, or like I said before, for lack of a better word, how frictiony the surfaces are. Take a look at this next chart right here. This is various different coefficients of kinetic friction. Now later on we're going to talk about static friction, all right, which is friction that causes things to not move, but right now we're focusing on kinetic friction. Friction that exists between two objects that are moving past each other. Okay, you'll notice that rubber on concrete, all right, it's a fairly high decimal, okay, 0.8. Why is that good? Well, because rubber and concrete are what make cars stay on the roads, and you actually want there to be friction between your wheels and the ground. Steel on steel has a pretty high coefficient of kinetic friction. Glass on glass, okay, we're getting less and less right here. Glass tends to be pretty smooth. Wood on leather, I wouldn't have guessed that. Copper and steel, rubber on concrete. Look, when it's wet, the coefficient of friction is about 1/3 of what it is when it's dry. That's interesting. That's a good thing to know for new drivers. Steel on ice. Wow, we're really dropping down right here. People who ice skate are glad for that because they want there to be as little friction as possible between the steel of their blades and the ice. Waxed ski on snow. Look, that's pretty small. Teflon. Teflon is I think it's a DuPont or Dow product that is very, very slippery, very little friction. Things slide very easily. And your synovial joints, there's actually fluid in your joints to let your joints move without any creaking or friction. Look how small that is. That's good because you don't want your joints to creak. So all these are different coefficients of kinetic friction. So now we're going to do an example. And we'll do this, and then that'll be the end for this section right here. Again, the first thing I'm going to do is I'm going to kind of put that up there so we have a little bit more space. Okay, just like that. And we're going to talk about this car. This car that apparently set the world record for the longest skid marks. That must have been kind of cool. But when you skid, that is when you brake hard enough, you're locking your tires. Your tires are no longer spinning, and so the brakes are locking the tires, and so what's really stopping you? Well, it's the friction between your wheels and the ground, right? And so it tears off rubber and it makes those black marks on the pavement, but at least it slows you down, hopefully, before you hit something that you were trying to avoid, all right? So the world record for the longest skid mark on any public road was supposedly 290 meters. All right, so let's go ahead and write that down first of all. Our displacement equals 290 meters. That's pretty ridiculously long. That's longer than 3 football fields, I think. And I guess it makes sense that a Jaguar or some sort of supercar was doing that. So the question is, how fast was the car going? That's interesting to know. When the wheels became locked. There should not be an apostrophe right there. When the wheels became locked. All right, so let's write down everything else we know. First of all, the mu k, that is the coefficient. Try this again right here. I'll write it up here. Coefficient of kinetic friction between the wheels and the pavement was 0.6. Okay, okay? No units, it's just a coefficient. What else do we know about this scenario right here? Well, we know that the final velocity, why is my pen, there we go. Final velocity is 0 meters per second, right? That's good to know. And we want to know what the initial velocity was. And that's what we're solving for right there, okay? So as this car is coming to a stop, okay, what is the net force on the car? What is the net force on the car bringing it to a stop? Now, the assumption is that once the driver has hit the brakes, he's taken his foot off the gas, so the engine is no longer propelling the car forward. But the car did have an initial velocity that we're trying to figure out. And so what's actually bringing the car to a stop right there? Well, the only thing that is bringing the car to the stop is the force of kinetic friction. All right, in fact, I'll just rewrite it right here. Kinetic friction between the wheels and the pavement, right? Oh, you know what? I think, oh, never mind. Okay, that is the net force that is bringing this car to a stop. Let's write that out in a little bit more detail, okay? How do we describe kinetic friction? Well, we said before, just a slide or two ago, that the force of kinetic friction is the coefficient of kinetic friction times the normal force, right? All right, let's go back to our diagram of the car right here. What would the normal force be? The normal force is the force that is supplied by the road to keep the car up, right? What does that have to be? Well, in this case, since the road is flat and we don't have any kind of slope right here, the normal force has to be equal and opposite to the weight force, right? If the car were heavier, more massive, then there would be more normal force. But the car has a certain weight, and so it's simply normal force is going to have to be equal to mg. So why don't we go ahead and write that in as well? So we can say, all right, well, really we can say the friction force that is bringing the car to a stop is mu k times mg. Now, you might be saying to yourself, well, wait a minute, we don't know the mass of the car. That's okay. We're going to find out that it really doesn't matter, okay? Secondly, let's write a statement for the net force on the car as a system, all right? Net force on the car as a system equals what? Well, we know it's always true that that equals mass times acceleration, right? So we can say, all right, well then our mass times acceleration of that car system equals what? Equals our friction force, mu k times mg. Why is it that the mass of the car does not matter? It doesn't matter because it will cancel out. It will cancel out, and so we can say, all right, well, then that means our acceleration equals m, not m, right? Equals mu k times g. All right, well, let's think back. What are we solving for right here? Well, we're solving for initial velocity, all right? We're solving for this right here. So if we have initial velocity and final velocity and displacement and acceleration right here, we should be able to solve for initial velocity because, after all, if acceleration equals mu k times gravity, let's find out what acceleration is and then solve for the initial velocity of the car. All right, what's our mu k? What's our coefficient of kinetic friction? That's 0.6, no units, right? It's just a coefficient. And of course, g is 9.81 meters per second squared. All right, what do we get for our acceleration right there of the car? 0.6 times 9.81, oops, 0.6 times 9.81, I did a typo. I get 5.9, all right? 5.9, try that again, 5.9 meters per second squared. All right, now let's think about this for a second, though. If the car is coming to a stop, this is the magnitude of the acceleration. What must be true of it? Well, that means the acceleration has to be in the opposite direction, right? We should really say that the acceleration is negative 5.9 meters per second squared because it's acting against the direction of motion. All right? So that's our acceleration right there. Now let's go ahead and just solve for the initial velocity. We say v final squared equals v initial squared plus 2 times our acceleration times our displacement, right? So we can say that our initial velocity is going to be squared equals v final squared minus 2 times our acceleration times our displacement. All right, let's now just solve for initial velocity. Initial velocity is going to be the square root of v final squared minus 2 times our acceleration times, that's a delta right there, times our displacement. Okay? V final 0 minus 2 times, good thing that acceleration is negative, right? Otherwise we'd have a square root of a negative right here. Negative 5.9 meters per second squared times our displacement, which was what, 290 meters. 290 meters right there. That's going to give us our initial velocity. So 5.9 times 290 to the square root, 58.5 meters per second was the initial velocity. If you were to calculate, if you were to transfer that to miles per hour, that'd be somewhere in the realm of 130 miles per hour. So that sucker was moving when he slammed on his brakes. So no wonder he skidded for 290 meters right here. So all this stuff down at the bottom, this is kinematics. You guys know this stuff. How do we relate it to what we've been talking about? Well, we relate it like this, that the net force, if the net force is friction, we need to know how to calculate that net force and turn that into values that we've been talking about, like mass and acceleration and so forth. So as you can tell, I'm recording at school right here because there's the announcement. So I will sign off, but if you have any questions, please make sure you come see me. Thanks a lot. I'll talk to you later.